Good day, ladies and gentlemen. My name is Bob Willis, and I'd like to take about 30 minutes of your time to talk about static control. And I don't want to just talk about it because that's no good at all. Every manufacturing company, every electronics company probably has some form of document, some sort of rule, some sort of regulations which say how you will handle printed circuit boards, how you will handle components, and how you will look after your area. Very nice, very good for auditors, quality staff, for reference source. But it's no good unless you employ some sort of practical training for the staff, for the people who actually have to handle the boards, use the components. And that's where static control and a presentation, a very basic presentation on the things that are required, must be undertaken. We have to look at each individual area of concern and talk about that, and actually demonstrate to people what can happen if static electricity is not considered. First of all, what is static electricity? It's a natural phenomenon that everybody can experience, whether it's at home, when you're walking across a carpet, for instance, and you come in contact with some metal object that might be close to or connected to Earth. If you're handling a piece of radio equipment, you may touch it and you might hear the cause of static are picked up on the amplifier. It's a very high voltage charge but very low in amperage, so it can't hurt you, but you can see it, feel it and hear it. And hopefully I'll be able to demonstrate those three areas for you. How is static caused? It's caused in a number of ways, but the most well known is the movement and separation of materials, called triboelectric charging. The triboelectric charging or triboelectric series is a flash name for a list of components, a list of materials. And the different materials that are available on the market, mostly the synthetic materials, can generate very large static charges. They can be either materials of the same like or different materials, two materials coming in contact with each other. They're arranged in a list and they're separated. Depending on how far they are away in this list, they will produce a large charge. If they're very close together, generally speaking, they will produce only a small charge. The materials can produce both a positive and a negative charge on their surface. Here we have a simple example of a plastic bag. And using this static locator, you can see that it has 860 volts present on the bag, a relatively low charge, and depending on the ambient conditions and how much you move, separate, twist, stretch the bag, you can produce a far larger charge on that surface. As I said, I obviously want to talk about it, but I want to demonstrate it as well. There's no point in just me talking, or perhaps if you had reference to the document that I was talking about earlier, that's not enough. Practical demonstrations. First up, I mentioned about hearing a static charge, and here's a simple demonstration. I've got a transistor radio here that's been tuned slightly off channel, and you know, well, the ladies amongst you, you know about television sets. They're a great problem. Due to the operation of a set, you can produce a very large static charge that's present on the screen. And every so often you have to clean the screen and remove the dust and debris that attaches to it. So here is a static source. And just by holding this transistor radio and bringing my hand into close proximity with the screen, you can hear a static charge. So you can hear it. And one of the interesting things is that it's gone through my body and been picked up by the radio. To see it as well, I've got a simple printed circuit board here with a liquid crystal display on. Very, very simple, contacts both sides. And simply by passing it to one of you in the audience, you'll be able to see either a charge go from my body to your body through this simple demonstration, or vice versa. So let me just try this. If you'd like to pass it to a next door neighbour, and rub your feet as you're passing it, or rub your... See? Lights up. So you can see it, feel it, and hear it. Thank you very much. And it's returned to me. Obviously a static charge present there. So we can see it, feel it, and hear it. Now to see it would take something like 5,000 volts. To hear it, I think it's something like 6,000 volts. That's the sort of order. But we're talking about very, very small static charges that can damage semiconductors. Why do we want to protect components? Well, in the electronics industry, things are getting smaller and smaller, as we're all very well aware of. And the geometries inside semiconductors are getting smaller and smaller as well. Here we have a simple circuit of active layers in a semiconductor, one part of a switching circuit with active layers on this side and on here. And separating these active layers is a very, very thin oxide line, very thin indeed, less than a micron in thickness, very, very thin. And a small charge, depending on the type of geometry involved, something less than 50 volts can quite easily damage a device like that. The interesting thing is that it doesn't actually make it totally non-operational. It can just damage it and change the working characteristic of that device. Here once again we have an example where one device has been damaged by a static charge. Now I could spend quite some time standing up here showing you pretty examples of damage to semiconductors, and you say, well, I kind of believe it. What I want to do is convince you. I want to show you practical examples and then look at the methods in which we can eliminate static. What I've got is a very short video section here where we're going to damage devices, and you'll actually be able to see what happens. We have a field-effective transistor linked to a curve tracer, and we're going to introduce a static charge onto this device, and we're going to see the effect. To generate the static charge, we're using one of these zero-stat guns that many hi-fi people use to get rid of static charges on records. On the scope here, we can see the working characteristic of that device, how it switches off and how it switches on. And this simple form I want you to remember. If you watch closely, you'll see that we're introducing a number of static charges to the device, but it only takes one to have the effect that I want to show. Here once again we saw the working characteristic of the device, how it switches off and switches on. Right, there we've seen it's changed, significantly so. If it wasn't working, it would be a straight line. But as you can see, it's still switching on and off, still switching on and off, a change from its original characteristic. That's an important thing to remember. Just one more demonstration on perhaps a more familiar package device, a dual inline device, a timer circuit. Once again, we're going to introduce a static charge onto one of the gates. Once again, you'll see the effect. Once again, you can quite clearly see the working characteristic of the device. And when we introduce a charge onto it, you'll see it change. The interesting thing about this is this device continues to change, continues to degrade its performance due to the static charge. Once again, it's still working, it's still operating, it's still switching, but the change has taken place on that device. There's a practical example how a static charge can affect a semiconductor. Here is this, the first device we saw, which was a field-effective transistor, and you can see a very small area that has changed on the device. That's about 100 times magnification. If we look 1,000 times magnification, you can see the sort of damage which has occurred between these two lines. In fact, if you relate it to a printed circuit board that you normally assemble these devices on, you call it a solder short. The next device, just in the corner there, between these two lines and a buried gate underneath, you can see a very fine rupture. Once again, that's 100 times magnification. If we look at it at 1,000 times magnification, it looks like a crater in the moon. A charge has gone right through the device and left rather a large hole in it. Component protection. What do we do? There are a number of things we do within assembly areas to protect components, either in the boards or during assembly, and I want to look at each of those individually. But first of all, let's look at the components. Normally speaking, components are all supplied in dip tubes, either conductive or anti-static at this moment in time, although there is a move to go over to conductive totally rather than just anti-static. And these are normally used with automatic placement machines, and affords the ability to automatically place the components directly into the PCB. We have assembly areas which, within the area, use a number of different methods of controlling static and protecting the components and the boards that we obviously have to supply to our customers. But how do we tell that a board contains static-sensitive devices? Well, depending on the company involved, there are different methods used. In this particular example, it's actually indicated on the board. It's actually written on the board surface, contains static-sensitive device. Consequently, people have to take special precautions when handling it, either at its assembly stage or after it's assembled during test or installation in product. Now, how do we know which components are static sensitive? Well, nowadays, with the introduction of very high-speed devices and the reduction of size of many styles of components, in time we'll have to consider nearly everything static sensitive. But you've got to classify the devices, and one method that is used is putting a letter which indicates static sensitive in the code for each device. A semiconductor might have a code CS and then the number of the device. In this particular case, an extra S is added, CSS, the extra S standing for static sensitive. So we're able to understand how the boards are indicated as being static sensitive and how the components are indicated as being static sensitive. So let's move on and look at the individual ways in which we can protect our components. In most assembly areas, we'll have conductive benches and chairs, we'll have wrist straps, conductive floors, heel straps possibly, and work coats. And each one of those particular items can afford protection to components. The most effective method of reducing, controlling, getting rid of static electricity is the wrist strap. Here we have an operator working a bench with an assembled board. She has a wrist strap on her wrist, making intimate contact with the skin. The lead is connected and then down, connected to the bench. At a closer view, once again we can see the strap making intimate contact with the skin. It has to work. The lead connected and down connected into the bench. And one of the other important things is the operator is holding the board correctly. Wherever possible, you should hold the board by the edges. You should avoid making any contact with the components themselves or the leads. Why do you want to do that? One reason is you can easily damage the delicate components just by physical contact. You can also introduce possibly a static charge onto the device. You don't want to touch the board surface either side because everybody may have contaminants on their hands and you don't want to introduce those onto the board. The other thing is there's lots of sharp leads underneath this board and I certainly wouldn't want to cut my hands on them, and I'm sure you wouldn't want to either. So it's important to handle the board correctly. As I said, the most important and best control of static electricity is the wrist strap. I'd like to do a little demonstration, if I may. Here we have one wrist strap. There are numerous different types available on the market. The most important thing is to assess which one is economically the best one for you, one that has a reasonable life, and also the ones that fit the operators. If they don't fit correctly, they will not work. So it's important to have the one that is correct for you. If you're wearing a wrist strap and it's too small or too big, then speak to your supervisor and ask him for a new one. It's important. A simple indication that that strap is working. A buzzer shows that a circuit is taking place. But if the strap is put over a blouse, a shirt, it won't work. Also, perhaps you're handling flux or solder, or you're using paint or something, and you want to put a pair of gloves on to protect your skin. Make sure that the strap is still making contact with the skin, and then it will work effectively. And if by chance you happen to have damaged your wrist, for instance, and you're wearing a bandage, once again, put the strap on the other wrist. It's easily done. Here's another type of strap that you can do up yourself to a certain tightness. It doesn't have to be too tight to cut off the circulation, it just has to be comfortable and to make proper contact all the way around. If it's hanging loose, it will not work effectively. Simple demonstration to show you that the strap works in theory by showing that it works in a circuit, but what I'd like to do is show you another little short video, and you'll see by this that a static charge can be dissipated through the lead. Here we have a gentleman, he's connected to this meter, and I think you can clearly see that he's producing a static charge. He's making the needle move to one side. This is in fact a center zero meter, and any deflection to the right or the left shows that he is generating a static charge. What he's going to do now is put on a wrist strap, as he has, connect himself to earth, and then try very, very hard to produce a static charge by shuffling his feet on a vinyl floor. And I think you can see quite clearly when he moves his hands that the needle is still in the center zero position. There's no deflection either right or left. I think you'll agree he's trying very, very hard. Now when he disconnects himself, once again he can easily produce a static charge. A simple but very effective demonstration that shows that you can produce a static charge, and the wrist strap is a very effective way of getting rid of that charge. We mentioned conductive tables and conductive chairs. Here we have a chair, and one of the most important things is that it's got to go somewhere. And in this particular case, it's standing on a piece of conductive flooring, and it has a metal foot to make sure that it makes contact. It's very important that that is there, otherwise one would be isolated from the other, and it certainly wouldn't be very effective at all. To look at a schematic, a diagram of me or you perhaps sitting at your place of work, obviously very active, this person, there's nothing on the table at all, but never mind. Here we have a conductive table, conductive flooring, conductive chair, and you can see the wrist strap. The lines indicate how a static charge can flow from the person down to earth and away. Now, I mentioned conductive floors. It obviously depends on the area that you work in, whether you have such a facility. But when you're walking around in an area that has conductive floor, everybody's shoes are different, and they tend to be an insulator from the floor. And what is required is some method of connecting this to this. Now, we could have a ball and chain, and I'm sure there's lots of people who would advocate that, but we have a very effective method. And if I can demonstrate this, a conductive strap. There are different types, reusable types available on the market, but here's just one method. And it's very important to see exactly how these should be fitted. Take this shoe as my example. The strap has a metal part inside which quite easily clips round the shoe. It's held in place. It wraps round the shoe. The loose end goes inside. It's got a contact adhesive on, so when pressure is applied on the base and on the side, it stays in place quite happily. And it is an extremely effective electrical contact between the sole of the shoe and the foot inside. As I mentioned earlier, there is other methods. We have a reusable type here that you can see can fit onto the back of the shoe and it's clipped over the front. And we also have one here for ladies with a toe grounder. They are a little bit more expensive, but they are effective, as these are. Now, a lot of people don't believe these things work. Well, they do. And hopefully, once again, a quick practical demonstration on this short video extract will show you that they do work. Once again, we can produce a static charge on the gentleman by shuffling his feet on the vinyl floor. He's wearing a strap on one shoe, and what he's going to do is generate a charge on himself and then stand on the conductive flooring, which is connected to earth, and you'll see the charge actually drain from his body. You can see quite clearly the needle flicking to one side, showing that he's producing a static charge. And by standing on the mat, that charge will slowly drain from his body down to that center zero position. The higher voltage drains very, very quickly. The last few volts take a little time to get down to that center zero position. Again, I think a simple, practical demonstration of how static can be produced and can be got rid of. Another important thing, I mentioned earlier about synthetic materials can produce large static charges, and here we have a synthetic jumper, and once again, a method of monitoring the static charge, and it shows 1,400 volts present on this piece of material. Now, obviously, we can't do anything about the different types of materials that everybody wears, because obviously the synthetic materials are becoming more and more popular. But we can cover them up. We can use a work coat. In this particular case, the young lady hasn't actually got it buttoned up. It should be buttoned up. And what that effectively does is cover up most of the areas that can produce a static charge. Now, one thing I'd like to emphasize is that, all right, by putting on the white coat and covering up the body, yes, you do cover up the materials that can produce a static charge, but I personally feel far more important is that I don't get any solder or flux or solvents or dirt on my clothes. I think that's very important. And it also protects you from dropping anything else on your clothes. So it does two things: protects the body, which is very important from a health and safety point of view, and it helps prevent static as well. Now, when we've made the boards and assembled them and soldered them, what do we do with them? Well, we obviously want to sell them. That's the most important thing. And we want to protect them. So boards, when they've been assembled and they're passed around either in the factory or when they're sent to the customer, should be protected. And here we have a conductive bag that the boards are put into. There are different types of conductive bag, and it just depends who the customer is, what requirements they may require. But when it's in the bag, it should be labelled to inform people that there is a board or components in there that are static sensitive, and it should be sealed in some way. Many other materials are brought into a working environment that are great static generators, and they may cause a problem. And from a cosmetic point of view, in a working environment, it's important to make it look correct as well. Make it look tidy. There's nothing worse than bringing a customer around if there's boxes and bits of paper everywhere. What we like to do is control the working environment and use one form of packaging material for documents, papers, and loose items in the area. And what we use is an anti-static material within the working environment to prevent other plastics coming into the area that can produce very large charges. We've obviously got to inform people with signs as they enter an area. So if they're not aware of the precautions that have to be taken, they should ask. We've obviously got to inform people with presentations such as this, and obviously our workshop practice or our procedures. But I think the practical presentations such as this are the most important. And it's two areas that I'd like to emphasise. Wear your wrist strap. It's the most important thing you can do. If you're walking around in an area, if you're a production engineer or a quality engineer and you go to a workplace, then you too should observe those same procedures. You should put a strap and a lead to the bench when you're handling the boards, when an operator is explaining a problem to you. If you're mobile in the area and you're using conductive floors in your area, then you should wear some sort of heel strap. And the most important thing, it's not just the production engineer's job, it's not just the quality engineer's job, it's our business. Static control is our business. My business, your business, everybody's business. Because if we don't control it from start of manufacture, from supplies of components, right to the end of the chain, we're wasting our time. It's got to be everybody's business. Static control. Thank you very much.